Hello all, welcome to lecture 37. So, we have been looking at surfaces and we have seen when surfaces are unstable. So, you can actually look at a polar plot or the inverse of a polar plot and be able to say what surfaces are stable, what surfaces are unstable, and turns out so except for so we will see more realistic polar plots, but except for the surfaces which have high Miller indices or surfaces that have especially since these polar plots have a lot of cusps, right. So, only surfaces at the cusp seem to be very stable and all the other inclinations sort of split up into the surfaces with cusps, right. So, that's the origin of what is called faceting in all these crystals. Okay. So, just just to recap what we did in the last class, so we said let us look at this inverse gamma plot in this PowerPoint. So let us look at this inverse gamma plot, and then in the inverse gamma plot so we can define the trajectory of what are stable surfaces. So for example, this point is a stable surface, any point here is not a stable surface, it is going to split up into B and C. This is stable surface, any point here is going to split up into D and whatever this label is, and so on and so forth. Okay. So so that is what it is. Now you can also translate the same thing, right. So you can also translate the same thing into real space or gamma space, not real space. This is gamma inverse space. You can also translate the same thing into gamma space, and in gamma space so this construction of a tangent so to these surface cusps, right. So here I am just constructing tangents and looking at overall trajectory, right. So overall trajectory of the tangent, right. So that turns out to be what is called a circle tangent construction. So you draw circles, you shrink these circles from the center of this gamma point, you shrink these circles so that they they tangentially touch your surface energy plots. And so anything which is outside of this circle is an unstable surface, and anything which is inside, or so the things that are not outside of this circle are stable points, right. So you can also do what is called tangent circle construction, right. And so once I look at it, so AB is stable, BC is unstable. So in fact any point between B and C is going to split into B and C, that is my faceting. CD is stable, any point between C and D is a stable point, right. But again, like I said, this is a surface, in this example so the surfaces are chosen such that C to D there is no huge cusp, but in reality so in real crystals of course there is going to be a huge cusp between C and D. Okay. So now you can imagine that if there are huge cusps like, or maybe I have this huge cusps like this, right. So very simply put, right. And then if I am drawing a circle from the center, a circle that passes through the center and tangential. So of course so the maximum tangential I can be is wherever these 2 points are hitting, right. So anything outside, so more everything so especially with such large singularities, everything outside of this singularity is an unstable surface. So any of these surface is going to split into this surface and this surface. Okay. So that's how I can understand why I have faceting in crystals. So right. So this is faceting in crystals is explained by so I can look at gamma plots or gamma inverse plots. Okay. So in gamma plots it becomes a tangent circle construction, in gamma plots it becomes just a tangential in gamma inverse plots it just becomes a tangent construction. Okay. All right. So now I will come to this very soon, but yeah. All right. So let us go back, and now so what next then, right. So I know which surfaces are stable, which surfaces are unstable, right. So most of these surfaces will split up into the 1 0 0 and 0 0 1, right. Now in general, right, so these are all 3-dimensional surface energy plots, right. So you can imagine that along a certain direction, okay, so I have 1 0 0, but I may also have a 1 1 0 right, but I will have so this is 0 0 1 and so on, right. So, now if I do a tangent circle construction, so unless the 1 1 0 plane is very sharply cusped, right. So, I can just do so with respect to this, so there should be a circle passing through this, right. So, still the 1 0 0 and 0 0 1, the way I have drawn the gamma versus gamma as a function of n, still the 1 0 0 and 0 0 1 facets are stable, right, until the 1 1 0 has somewhat of goes and touches this, right. So, 1 1 0 energy should be very much comparable to 1 0 0, only then you will be seeing even 1 1 0 facets coming up, right. So, if it is not, then you do not see it. So, it all depends on the value of gamma, right. So, what is the value of gamma determines which facets you are seeing and which facets you are not seeing. Okay. Now, we also said in case of isotropic materials, if you remember, okay. So, we said that look, okay, so I have gamma as a function of n, right. In an isotropic material we have nothing like so I can do again a tangential construction, a circle tangent, and then all these surfaces are equally stable or equally unstable, right. So, all surfaces can exist, and so this actually translates to the shape of the crystal, which is R of n, okay. That is also spherical, right. So, gamma of n translates to the shape of the crystal. Why? Because gamma by R is a constant, right. So, that is 2 delta p, sorry 2 delta p by 2 gamma by R is a constant, okay. So, just because there is an internal pressure of this sphere, right. So, and so if I increase the gamma, then to maintain the same internal pressure I have to increase the R. So, but the shape remains the same, right. So, the shape remains the same. If gamma n is isotropic, R n is also isotropic, okay. Now, I am saying in a solid or in an anisotropic material, what will be the shape of the crystal? So that crystallizes in bulk, let us say that crystallizes. What will be the thermodynamic shape? So, in some sense so I have a liquid of material and I am going to make the first crystal, right. So, I am going to crystallize it in bulk, right. So, ideally crystallization happens at surfaces, right. So, that is called heterogeneous nucleation, but so for the sake of argument I am saying that so for some reason I am just going to crystallize this material in bulk, right. So, when I am crystallizing this material in bulk, this crystal, all crystals have shapes, they are not spherical, right. So, if the surface energy is uniform everywhere, if the surface energy is isotropic, then I get a spherical crystal, but surface energies for crystals are not isotropic, right. Gammas are anisotropic. So, I ask the same question, what is the shape of the crystal? Or in other words, I say if I know gamma as a function of n, right. So, can I predict shape of the crystal, okay, and this sort of a construction, right. So, in an isotropic case it is simple, right. So, it is just sphere, whatever is the shape of gamma will be the shape of the crystal, gamma of n and R of n correspond. In an anisotropic crystal also they should correspond, right, because effectively so I have a crystal, let us say with some phase facet, but that crystal has an internal pressure and that internal pressure is greater than the external pressure again, right, and Pc minus Pv is 2 times gamma n, depending on which facet I am looking at, divided by Hn. Hn is the radius or the height of it from the center, okay, height of the facet from the center. Okay. So, 2 gamma n by Hn, this relation is also true, essentially this is also true. Okay. So, my gammas and Hs of various facets should be in such a way that gamma n by Hn should be equal to Pc minus Pv. Okay. So, and then you can see that if I have gammas that are faceting, right. So, then Hn also should facet, right, and Hn as a function of n, that gives me the shape of the crystal, right. So, in fact, so you can look at the derivation of it from a book called Markov, right. So, I need my crystal to be, so the derivation goes like this: the crystal should be in equilibrium so dF equal to 0, right, and also so I am not changing the volume of at a given volume, right. So essentially I am doing the same calculation, right. So, for a given volume, what is the equilibrium shape? For an isotropic material, that is a sphere. For isotropic material, that is a sphere, but I am saying for anisotropic material, what is it? Okay. So, and then so you have so P dV, which is delta P dV of the crystal, plus sigma gamma n dAn, right. So, for every facet that should be 0, this is essentially dF equal to 0 condition, okay, and this will yield your gamma n by Hn as a constant, and that is nothing but my internal pressure or 2 times internal pressure, okay. So, essentially gamma 1 to gamma 2 to gamma 3 to gamma 4 and so on to gamma n ratios should be the same as H1 to H2 to H3 and so on all the way to Hn. So, if I know the gammas of all facets, I can say that, okay, so this radius or H is in the ratio of gamma 1 to gamma 2, right. So, this facet is here, this facet is here, H2 may be larger because gamma 2 is larger, H3 may be smaller because gamma 3 is smaller, and so on and so forth, right, and that determines the facet, the shape of the crystal, okay. So, that is the idea, okay. So, now this is just the theory, right. So, this is the theory, but then so you can look at what is called a beautiful construction called Wulff construction, that puts this theory of 2 gamma by H being a constant or being the internal pressure, right. So, that puts the theory of into a visual construction, okay. So, and that construction is as follows, right. So, I okay. So, that construction, yes. So, I actually take the gamma, so gamma n of n, right, and so wherever I am actually going to draw the normals, right. So, for example, if I am at B, right, so I am going to draw a normal to B, right. So, if I am at C, I am going to draw a normal to C, right. So, similarly, so wherever I am at this gamma n of n point, I am going to draw just the normals, right. So, and between B and C, of course, there is nothing, right. So, so I am not going to I mean, so any point between B and C is just going to split as B and C, right. So and then so if I am here, I am just going to draw normals, right. So, if I am here, I am just going to draw normals and so on, right. So, like that I am just going to draw normals to gamma, right. So, gamma of n, I am just going to draw normals to gamma of n at whichever point, and the trajectory of all these normals, sorry, the internal you know, so lies completely, okay, so that is the tangent circle theorem, but you know, so the internal trajectory of all these normals gives me a shape of the crystal. So for example, this gives me the minimum shape, this gives me the shape, and you know, so how am I calculating the shape? The calculation of the shape comes by minimizing gamma dA, and that is what we said, right. So gamma dA is minimum for or df equal to 0, that is essentially what this means for a given volume. Okay. Now you can actually see this construction, I mean, so here it becomes slightly harder to understand because there are so many of these normals, right. So all these normals are trying to intersect each other, but you know, so I am actually drawing normals only for the stable positions, right. So I have constructed this stable diagram, right. So these are the unstable positions, this is stable, this is stable, this is stable. I go here, I draw the normal, I go here, I draw another normal, I go here, I draw another normal, I go here, I draw another normal, right. So like that I am drawing normals at all these stable positions, right, and then I look at the trajectory, I mean, so I look at the internal envelope of all these normals, right. So that is essentially what I did here. So if I look at the internal envelope of all these normals, that gives me a shape, right. It's ideally, you know, so because my surface energies are nice and not very cuspy, right. So I also get a shape that is sort of well rounded and things like that, right. So it's not really nice facets, right. So here, because of this example that has been taken, you know, I get shapes which are well rounded and things like that, okay. But you know, so essentially what I am minimizing is gamma dA, right. So I am not just minimizing gamma, I am minimizing gamma dA. This is something to remember for a given volume, okay. All right. And you know, so this is what lets this happen, right. So gamma, you know, so whatever is the gamma is the height, right. So gamma and height of that facet are proportional to each other, gamma and height of this facet are proportional to each other, gamma and height of this facet are proportional to each other, and that is what lets me draw these tangents, right. So that is why this tangent construction works, sorry, not tangent, the normal construction works, okay. So and then I am actually looking at the trajectory of all these normals, okay. So now let's take more realistic you know, surface energies, though they look somewhat like this, okay. So I have, you know, so there are all these surfaces with, you know, slightly lower energies, but you know, so there is a major surface here, major low index surface. So the surfaces where there are cusps, typically in FCCs these are 1 1 1, in you know, so these are all low Miller index planes. We saw that, right. So 1 0 0 less than 1 1 0 less than 1 1 1 for causal crystal, for FCC 1 1 1 less than 1 1 0 less than, and so on, right. But these are all low Miller indices, you will never see 31 1 73, okay, as a plane with the least surface energy. No, this is not possible, okay. So this is never seen, okay. So typically, you know, surfaces with low surface energies, gammas, have you know, also low Miller indices. That is why whatever crystal you see, right, these crystals are typically terminated by 1 0 0 or 1 1 0 or 1 1 1 and so on and so forth, right. So nothing fancy, I am not terminating a crystal with 10 to 330, okay. So that is going to be a very unstable crystal or unstable facet, that will again, you know, sort of split itself up into these low Miller index surfaces, that is very important, low Miller index surfaces, okay. So you know, so let us do the Wulff construction here, you know, so I have my stability points, right. and so I'm just going to draw my tangents or my construction here. So I'm so at this point I draw a perpendicular, at this point I'm drawing a perpendicular, at this point I'm drawing a perpendicular, like that I'm drawing all sorts of perpendiculars, and I see that this is the trajectory that wins over all the other trajectories, right. So this is the envelope of all the trajectories. Okay. So the crystal shape that I get is here. Okay. Now you may wonder, okay, so A1 however has the least surface energy, right. So A1 has a larger cusp than A2, right, but in the shape of the crystal I am also getting a part which is A2. Okay. So I am getting both A1 terminated surfaces and A2 terminated surfaces. Right, from the Wulff construction, so okay, so I can, wherever there are cusps I am still trying to draw, right. So there is some stability diagram, right. So on the top of this, so I can just say that, look, okay, so there is some stability diagram like this, right, but so all these cusps will be a part of the stability diagram, right. So I go to these cusps and then I draw the normals, but you can see that wherever I draw the perpendiculars, not the normals, right, but I see that eventual shape will be a superposition of all these, or it will be the not the superposition, but the internal envelope of all these normals, right. So that is this, the internal envelope of all these normals is this, but then in this case you actually see that A1 although has least surface energy, gamma of A1 is less than gamma of A2, but I see that both A1 and A2 are terminating the surfaces, it is not just A1. Okay. Now why is that the case? That is the case because it is so typically what surfaces terminate a crystal? So it is not the computation of gamma, gamma is not the most important parameter. Right. So ideally you can say, look, 100 has the least surface energy, so I should always get cubes, right. So so in a causal crystal, right, so if I do the Wulff construction, I should always get cubes. Because gamma 100 is the least, right. I want to always end my surfaces with least surface energy planes, right. So you would intuitively think that that is the case. I want to terminate the surfaces with least surface energy planes, but that is not the case, right. So in fact least surface energy is not the criterion, the criterion is gamma dA, which is G capillary, that should be minimum, or F capillary or G capillary, right. In other words, dG capillary should be 0. Okay. So and this is what we did essentially, you are minimizing gamma dA, you are not minimizing gamma, right. So minimize gamma dA and not gamma per se. Okay. And because of that, sometimes it is not just 100, I may also get a 110, right. So I get a 100, but I may also get a 110, right. So I get surfaces which are always so, but you see that the 110 percentage is less, right. So this will be the most optimal combination, right. So I take help from a slightly higher surface energy plane, right. So and not just all planes which are just 100, right. So this is a more optimal configuration. Than so maintaining the same volume but expanding the 110s, right. So than this, for the same volume. Okay. So, this is slightly deep, right. So, I am of course, there are, let us say, smart people. Okay. So, I am not always optimizing my work by selecting the smartest people, right. Okay, you are smartest, but then I also want people, I mean, so I can compromise a bit so that the eventual free energy function, right. So, eventual way in which I interact with them, right. So, with all these people, right. So, I'll also look for people who are more human, right. So, who have so who are more social, let us say, right. So, that the interaction becomes easier and things like that, right. So, especially if I'm a job giver, right. So, let's give that example. Okay. So, if I'm a job giver, you can have the strongest resume, so I'm not filling my team with people that have the strongest resume. The strongest resume people are there, right. So, they are the 100 planes, but in order to optimize my overall social interaction, I will also give jobs to people whose resume is not the strongest, slightly weaker, but so overall for the optimization constraint of whatever it is, right. So, in this case this is dg equal to 0, in my case it is some kind of a social interaction that is going to be much better. It is not just the strongest resume, it is also slightly weaker in professional resume, but in terms of the area it is smaller, right. So, in terms of the resources that I allocate, it is smaller, right. So, something like that, right. So, there is always a compromise, and that compromise comes because the overall function I am going to minimize is dg equal to 0. It is not, I do not want to populate my phase for a given volume of the crystal, right. So, I do not want to populate my facets of the crystal with only lowest surface energies, right. Lowest surface energy is not the criterion, the lowest capillary energy is the criterion, or dg equal to 0 is the criterion, and because of that, so I can have facets with lowest surface energies. They of course mostly populate my crystal, but I can also have facets with slightly higher surface energies, such as the 110 planes or the 111 planes in a causal crystal. Okay. So, the equilibrium shape will have facets which are not just facets that have lowest surface energy. Okay. Okay. Now, this is better exemplified so in this example, right. So, if I take an FCC crystal, ideally in an FCC crystal, so I have an octahedron of 111 planes. So, 111 planes just make an octahedron, right. So, 1 2 3 4 facets on the top, 4 facets on the bottom. So, ideally I would say that okay, this is the this should be the crystal that is an equilibrium configuration. Okay. But turns out, if I take the help of some of these 110 planes, okay, so if I cut this off and take the help of some of these 110 planes, give them lesser area, that is okay. The volume is maintained constant, I will give them lesser area. Such a crystal has a lower total capillary energy, okay, than this crystal. Okay. So, the equilibrium crystal shape of an FCC crystal is a bunch of 111 planes, but also in lower proportions 100 planes, right. So, this will be the equilibrium Wulff shape, what is called the Wulff shape of an FCC crystal. Okay. So, it is not this. Ideally, if you are just minimizing surface energies, you would assume that this is the shape, but I am not just minimizing surface energies, I am minimizing the total capillary energies, and then turns out this shape which is a dodecahedron, right. So, it is more closer to a sphere than these sort of facets with this sharp pointed facets, right. So, this is a much more nicer or equilibrium shape that minimizes the G capillary than this. Okay. So, that's the understanding, all right. Okay. So, so that's that's the discussion on Wulff crystals. So, essentially so if I am making crystals or so in any nucleation process, if the crystal is just nucleating from not on surfaces, right. So, on surfaces we'll go to interaction of interfacial energies and things like that in the next class. But so if there is any crystallization process, if the crystal is smack nucleating somewhere, it has to form surfaces, right, and these surfaces if it is all thermodynamically nice and nice and good, then they will start taking what is called a shape, what is called a Wulff shape. Okay, and you can predict the shape of these crystals using Wulff construction. Okay, all right. So all crystals, crystals have shapes because their surface, fundamentally crystals have well defined shapes because their gammas or surface energies are anisotropic. Okay. Polar plots are very cuspy polar plots, right? Cuspy polar plots. Okay, and that the shape of the crystal is given by Wulff construction. All right. Now, and this is the equilibrium shape. So if I'm doing some crystallization in a thermodynamically almost a quasi-static conditions, then I get these equilibrium shapes. Okay. Now, so there is a faculty member, there is a very one of the very smart material scientists so that I have ever interacted with. His name is Professor Ravi Shankar. Right, one of the very great and very good material scientists. He also does electron microscopy in his research. Right now, Professor Ravi Shankar is also my colleague from IISc. Right now, Professor Ravi Shankar actually makes these nano crystals. Right, so these so if I'm making nano crystals, the idea is so I have surfaces, right? So I can do reactions on the surface. So I can use these nano crystals. So I have large so especially if the crystal is nanoscopic sized. So there are enough surfaces that I can do chemical reactions on surfaces, and I can use them for catalysis and things like that, right. So he works on this very nice area field of catalysis, and so they have to make nano crystals of sizes and shapes which are sort of predetermined, right. So for example, let's say the Wulff construction says that, look, you should get a dodecahedron. I am growing an FCC platinum, right, in the form of a nano crystal, right, and the Wulff construction says I should get this dodecahedron with the 111 facets and the 100 facets. Okay, but a dodecahedron is not good for reasons I don't know, right. So I want to have some controllability over the shape. Okay, so if I want to have some controllability over the shape, and let's say I want to actually make not dodecahedrons, but I want to make cubes. Okay, so I want to make cubes, platinum crystals, not dodecahedra. Then what I should do is I should so all the all the 001 planes, right. So all the 001 family of planes, right. So this is 100. If I terminate this crystal with 100 family of planes, then I get a cube, right. Okay, but so the 111 has low surface energy, so this is not an equilibrium Wulff shape, right. So if I want to get a cube, right, so a crystal as a cube, what should I do? I should actually then, if I want a cube, I should somehow decrease the gamma of 100 surfaces relative to 111 surfaces, right. So this is just a design constraint. This is the surface design constraint, right. And how do I do that? I should be a nice chemist, right. I will use what are called surfactants, right, that modify the surface, right. So, for example, the surfactants adsorb onto the 100 surface more than the 111 surfaces, let us say, okay. And then so they reduce the energy of the 100 surfaces more than the 111 surfaces, right. So there is a magic of chemistry that goes in there, right. So I can actually tune these surfaces, although the Wulff construction says, so if you do nothing to the crystal, it will form a dodecahedron, but I can use some chemical surfactants, right, and make some surfaces more, so it's like making surfaces hydrophilic and hydrophobic, right. So I can actually treat some surfaces with plasma and then make them more hydrophilic than they really are, right. Similarly, so here also I can treat these surfaces with some surfactants, chemical surfactants, right, increase their bonding potential, and so the gamma of 100 reduces compared to the gamma of 111, right. So we'll see how so the bonding, increasing the bonding potential reduces the surface energy, right. So I'm increasing the binding energy will reduce the surface energy, okay. We'll see that, we'll have a small equation in the upcoming classes when I'm going to look at interfaces. From surfaces we go to interfaces, but yeah, so and then I can selectively reduce the gamma of 100 with respect to 111, and then what I end up getting are these cubes of platinum and not really dodecahedra of platinum, okay. So I can do some shape engineering depending on what I really want, right. So let's say my reaction will happen more nicely on a 100 facet rather than a 111 facet, then it makes sense that I grow cubes of platinum, right. So is well catalyzed on a 100 facet than a 111 facet, right. Then it makes sense that I grow cubes of this thing, right. Or my reaction does not like charged surfaces, right. So if I'm growing titanium oxide, the 111 facet of titanium will have some charge, it has some polarity, but the 100 will not have polarity or charge, right. So my reaction does not prefer to have charged surfaces, then I have to grow 100 surfaces, or it prefers to get charge from the already charged surfaces, then I have to grow 111 surfaces, right. So I should do some shape engineering, and the shape engineering is done through what are called hydrothermal processes and some kind of chemistry that goes in, okay. And so if you go back and look at the research of Professor Ravi Shankar from ISC, so he has been doing all this sort of engineering for a long time, and so you can look at some of his papers and see how these cubes are formed, how these nano wires are formed, so you can engineer the anisotropy in ways that you want, okay, with a basic understanding that the equilibrium structure should be a Wulff structure, should be given by Wulff construction, and so beyond that, so what I do should be surface modifications, that's where the surface chemistry comes in, okay. So that's beyond thermodynamics, but again, from a thermodynamic perspective, I am reducing the gamma of 100 with respect to 111, so that the cubes become more feasible than the other shapes, okay. All right. So with that, let's conclude here, and in the next class we will go to more sort of interfaces, essentially so what are the interface energies and how do materials bond with interfaces that they like, with interfaces that they don't like, right. Again, we will go back to the example of water on a surface, right. So if the water likes a surface, so it's an isotropic material on a surface, and then extend it to an isotropic material. But before that, we will do a small problem, right, and the small problem is, okay, another so slight digression, but then so we want to understand, okay, so if I really make these crystals nanoscopic or so particles nanoscopic, what happens to the melting points of these particles, right. So we will do that small problem and then go to the interfaces, okay. So with that, let me conclude here, and I'll again see you in the next class. Thank you very much.